皆様ご着席いただけましたでしょうか。それではこれよりプログラムを再開いたします。オープンソースでここまでできるコントレイル設立者が語るオープンコントレイルとオープンスタックによるクラウドネットワーキングと題し、ジュニパーネットワークス株式会社クラウドプラットフォームソフトウェアソリューション部門バイスプレジデント兼ジェネラルマネージャー元コントレイルシステムズ社 CEO アンカーシングラ様にご講演をいただきます。なお当セッションでは同時通訳がございます。チャンネル1番で日本語をお聞きいただけます。同通レシーバーがお手元にない方はスタッフがお配りいたしますので挙手をお願いいたします。恐れ入りますが同通レシーバーはご利用後退出される場合には会場出口にありますカゴの中にご返却をお願いいたします。それではアンカーシングラ様どうぞよろしくお願いいたします。
So thank you, and I'm very happy to be here and talk to you guys. I was in morning with our general manager from the Japan team, and he called it SDN, Snowy Day of Networking in Japan, and it's quite unusual for Tokyo. So I thank you for your time and coming out here. What I'll do is I'll talk a little bit about OpenContrail. Juniper acquired my company in 2012, and since then we've been working very hard in building a full neutron stack for networking, which basically includes switching, routing, and a bunch of other features. And I'll talk a little bit about that as we go along. So, if you look at all the way from 2000, it seems like that 2001 to 2010 was a lost decade in networking. There's a lot of innovation happening at Facebook, at Google, at Amazon, and it seems like networking was not keeping up with it. All we were focused on was building bigger and bigger systems. And then it seemed like in the entire decade, all we could come up was better logos. Cisco came up with a better logo. We came up with a better logo. It was a decade of new logos. But again, in 2011 to 2013, we were still lost. All we could think about was, let's separate out control plane from the data plane. And that was a rage of the 2 years of OpenFlow. It was a solution that was actually looking for a problem. And it did find a few, especially in the data center networking. It did find a good or a relatively decent solution. And I think there's a lot more that can be done from here on. So what I think is in the next 4 years, what I want to focus on is really building to the Web 2.0 level of technologies into networking. And that's what I'm going to talk about a little bit. So if you look at networking systems, they're individually managed. And they're usually managed as through CLI or managed using a web GUI. And most of these GUIs or CLIs are managing individual nodes. But if you look at a Web 2.0 style system, it's a complete system level management. You do not manage individual nodes. You don't manage individual components, but you manage a complete system. That's something the networking never learned. The second thing we did was for everything, we had a bigger box. Bigger box was a solution to everything. Scale up has always been the name of the game. And Web 2.0 companies are always working on scale out. And that's something that networking really needs to get hold of if we want to solve customer problems in a cost-effective manner. The next thing is basically hardware systems. So all we could do was deliver each of the nodes as a hardware box. If you wanted a DNS system or you wanted an IPAM, it came from Infoblox, which should really be a software company, but all they did was sold you a big box. If you look at us, a firewall would come as an appliance. And the problem with that is that every time you want to upgrade a system, you basically have to get a new box. And it's extremely expensive, and there is no concept of virtualization, the ease of upgrade, ever thought from networking point of view. And last but not the least is the amount of visibility from networking systems has been very, very low. The best we could do was NetFlow and SNMP. It really is very limited visibility, and it's polling-based system. It doesn't give you historical information of what happened in the system, and debugging is also very hard because typically you have to reproduce the same problem again and again to get to the root cause. So what we really need is something like a big data analytics solution built into the networking stack so that you don't have to debug problems after they have happened by reproducing them. You should actually be able to go and replay the same problems. And that's something that really needs to be built into the networking stack from ground up. So in a nutshell, there are 4 problems with the networking stack today, whether it's OpenStack or any other networking equipment. That is a real problem that needs to be solved. It should really be automatic, it should be programmatic, and it should be a very scalable system. And from a customer point of view, I'm sure you're familiar with this. Building a data center, especially a legacy style data centers, is all about clusters, having the right cluster size. Even if you use enterprise virtualization technologies like VMware, the cluster sizes are small, and the applications reside within the cluster size. And if you have different departments or different applications that need to span clusters, it's very hard, especially from a networking point of view. Either you can't reach the VLAN, or the entire IP addresses cannot actually span clusters because your routing table limitation of having single tenant, having non-overlapping address space. So it's a big issue as far as building large cluster sizes is concerned. And if you look at how people want to build a Web 2.0 style data center, is any application can reside anywhere. If you need more instances, if you need the compute to reside anywhere in the data center, if you want the storage to reside anywhere in the data center, you need full cross-section bandwidth. And all the networking primitives, whether it's a VLAN or the policies for that VLAN or for that application, needs to show up where you're going to schedule the application. And it should not be tied to the cluster size. And that's why you need network virtualization, a scalable system that can solve this problem. So scalability is extremely important, and it has to be done in a programmatic manner. Especially using OpenStack, you cannot expect to have a CLI and configure a system. It should be all done using Neutron or Neutron APIs. And at the same time, one of the other big problems we saw is inserting services. Even if you use firewall as a service or load balancer as a service, you still need to have a mechanism to construct the VLAN so that traffic can go in and out. And what we want to do is completely automate that entire process. Be able to create virtual networks on the fly, containerize a service application. It should not even require re-architecting the application of the service to insert it in the path. And also the other thing is hybrid cloud should be very easy to build. That is actually a very hard problem to solve. And it's not just about having an L3 VPN connectivity or a IPsec VPN connectivity. It's also about hybrid cloud orchestration, management, security policies, and also sharing the right amount of information, not too little, not too much. And these are problems that we have to solve as an industry. So from an OpenStack point of view, we are used to building legacy data centers in this manner, where basically you have servers and VMs running in the servers, and typically you'll have an L2 switch, whether it's a vSwitch, a Linux bridge, or an OVS. And the problem is that these switches connect to TORs, and those TORs will typically connect with a layer 2, layer 3 boundary using a lag or a multi-chassis lag if you want to use all the links connecting from the layer 2 to layer 3 boundary. And then the problem is that you have a management headache. MC lag or redundant trunk groups are very, very hard to manage. And when there is a storm, it's very hard to prevent problems. So what basically people are doing is moving to a layer 3 clause, and I'll get into that as we get through this presentation. Your VLANs now cannot span the clusters. The clusters are the boundary for your VLAN because your layer 3 boundary is in your aggregation layer. So you cannot even have overlapping address spaces because you have a single routing table. So you cannot do multi-tenancy in this environment. If you go back here, because your VLAN is not spanning layer 3 domain, you have an extension problem of how long the application, how many VMs for an application can span the cluster. You actually also cannot use an overlapping address space because the address space requires a different routing table per tenant. So that has also been solved. We actually solved this problem for a few customers, but this requires a PE router sitting in the aggregation layer, which basically presents a VRF per customer. And as you know, having a PE router is expensive, And then you have an MPLS core, which basically makes it extremely hard, and troubleshooting is also very hard in this environment. So we basically thought, why not move the PE router straight into the hypervisor? So that's basically Contrail. Now if you look at modern day data centers, you want to connect the server directly to a layer 3 fabric. So now your switch is connected to a layer 3 boundary, and you cannot have VLANs directly sitting on this L3 network. So the way to solve this problem is people build VXLAN. And if you look at VXLAN, it's a great tunneling technology. It solved the tunneling protocol problem, but it never really thought about the control plane aspects of actually distributing the routes. So for example, on a blue network, if I want to reach from here to another VM on this network and I send an unknown unicast, I need a multicast tree in the fabric. And managing multicast is hard. So one of the big limitations of VXLAN without a controller is that managing the fabric becomes very hard. You need a lot of multicast trees, and it also is very hard to troubleshoot if there's a problem. The other issue for VXLAN is who's going to do routing. Where are you going to do routing from one VXLAN to another? And that typically can be done in two manners. One is you basically use software routers. It's basically what Nova Router does in a way. It basically routes for every tenant. And you can even use a VM providing the service, and that's exactly what a layer 3 gateway from some of the competitive solutions do. It's a big problem because now you are limited by the bandwidth from this VM. So that's one of the problems with Nova Router, is that the whole performance of traffic going from one virtual network to another is limited by the capacity of this virtual machine. And it's expensive because now you're doing routing in a place where you're burning CPU cycles, which could have been done at the edge. The other option is to actually build the VXLAN routing capability into the spine layer itself. And there are people doing that. Obviously, we support that as well. Cisco is doing that, and a bunch of other companies are also doing that. The problem with that is, again, you need a concept like VRF. Because if you want to use multi-overlapping address spaces, you really need to have a routing table constructed per customer, which is what the namespaces in Linux is trying to do here. You're having different virtual router per customer. So in a nutshell, it's actually not very good. The situation still is not very good. So what we thought is, it'll be great if you actually pull the router, a multi-tenant router, straight into the hypervisor. So why just a switch? The amount of processing power that is required to forward a packet is pretty much the same, whether I'm doing bridging or routing. So why not make the vSwitch a full-blown L3 VPN or L2 VPN router itself? And that's what we're proposing, and that's what we've actually open sourced recently, is a full virtual router running in the hypervisor. It provides all layer 2 and layer 3 VPN capabilities, in addition to lots of other stuff we'll go into. But again, you don't manage all of these routers individually. Now the big advantage of this solution is I can route straight from the hypervisor. I can bridge across tenants, bridge within the tenant and route across tenants or route across VLANs straight from the hypervisor. Your latency is reduced. Your overall cost of running the system is significantly reduced as well. And I can do NAT straight from the virtual router as well. So you don't need a NAT gateway. You don't need a NAT server. That's another big advantage of doing something like this. So what does Contrail do? Where is Contrail fitting in OpenStack? So if you look at OpenStack, Neutron serves all the APIs for networking. What we do is we basically have Contrail as a plugin into OpenStack, or OpenContrail as a plugin into OpenStack, and it provides full Neutron compatibility for you to provide virtual networks, for you to do policies, for you to do security groups, NAT, floating IPs, and stuff like that. Now the thing is, Contrail will not configure the switches in the middle. The whole goal is you basically have very small, limited amount of configuration in the fabric. The fabric is actually very, very simple, it doesn't do a lot of stuff other than move traffic from one server to another. It only has a limited routing table for moving traffic from one server to another. It doesn't have any tenant level information. And how is OpenContrail constructed? So if you look at the very bottom, it's a complete scale-out system. From the virtual router, you just keep adding more and more compute nodes. Each of the compute nodes will have a virtual router instance running inside it. It's running in the hypervisor. For every 2,000 nodes, for every 2,000 compute nodes, you need 2 control plane nodes. And as you add more 1,000 nodes, you just add one more control plane node to basically manage all the routes, manage all the topology, manage policies. And then configuration nodes are basically sized depending on number of APIs per second you want to serve through the configuration system. So if you're making lots of changes per second, then you just add more configuration plane nodes. Typically, our estimation is that for 10,000 servers, you should not need more than 2 nodes for providing all the configuration services. On the analytics subsystem, which is a third dimension of this problem, there are three sizing issues. The first one is the amount of data I have to ingest from all the nodes that are sending data or sending information to the analytics node. The first one being the compute node, the virtual router. It sends all the application level information like CPU utilization, it gives you memory utilization, what flows were generated, what is the jitter, what is the latency on the flow. All kinds of information is deposited into the analytics engine from the compute node itself. In addition, the control plane node, the configuration nodes, and all the other nodes in the system deposit all state changes, all state machine changes into the analytics node. It's done so that you can replay in case of an error. Let's assume somebody comes and reports a bug. One of the biggest problems is sitting down and saying, let's figure out how to reproduce the problem. It would be better if you can just replay and see where the state machines are stuck. And that's what you can do with this analytics system. You can go into all the state machines and see the state of the system at the time the problem happened. You can also use this in conjunction with CLOmeter to build a very advanced SLA solution, a billing solution, a metering solution. All of that can be done using this analytics engine. The other dimension of the sizing is how many APIs per second you need to serve for your UI. So we have built a fairly rich UI which we keep adding more and more features to for visualization. And the number of nodes will depend on what kind of APIs per second you need to serve out of this. The third aspect to the analytics node is how much data you want to store. So if you want to store a lot of data, non-aggregated data, then you will not need a lot of disk. And it all depends on the amount of VMs running, amount of traffic being generated, and those kind of things. So you really have to think about sizing of the system based on your needs. And all of these are basically controlled using APIs. We have all the Neutron APIs. We also have extensions, which are now being worked with the rest of the community to, especially for Juno timeframe. We're working with the Neutron committee as well in order to upstream some of the changes for the policy extensions we have done and things like that. From the services point of view, we can do NAT, we can do switching and routing in a multi-tenant manner straight from the virtual router. So you don't need anything else. You basically just need virtual routers and the config nodes and the control plane nodes running. So you will not see any gateways in this solution. The gateway is actually part of the solution itself. IPAM and DNS is built into the system, so you don't really need an external IPAM engine. You don't need a DNS engine. Obviously, you can use external DNS subsystems. You can use an external IPAM solution, but it comes built in. You can do load balancing straight from the hypervisor as well. It's especially useful for non-SSL, SLB kind of application. It's an ECMP consistent hash load balancer, and it is not just a web balancer. It can actually let you create your own service monitoring so that if you're load balancing traffic on the other side, it doesn't have to be a web VM or a web service. It can run on any kind of service. For example, if you're building a scale-out firewall service, then the other side is not a web service. So a traditional load balancer is not going to work. So what you can do is you can actually add service monitoring capability into the load balancer so that you can monitor the other side and you can do your own extensions. All the security services from both Juniper and third party are supported. For example, we support DDoS Secure. We provide web applications security as well, which is more of a intrusion deception system. And we provide a full stateful firewall as well in the solution. And you can obviously use a checkpoint device or an F5 load balancer or whatever have you. The other thing that we didn't talk about was high availability. Everything in the system is built from the grounds up for high availability and ISSU. So every control plane node has multiple configuration nodes that it talks to. And if any of the configuration nodes disappear, then the discovery service will give it a new configuration plane node. Each of the compute nodes that are running the virtual router talks to multiple control plane nodes. It learns routes and policies from multiple control plane nodes. And if any one of them were to disappear, it'll get connected to another control plane node. And the same thing for analytics. And in addition, if you go back to this slide, since we use protocols and not non-standard APIs between the control plane nodes and control plane node to configuration plane node, for example, between control plane nodes we use BGP, between control plane node and config nodes we use IFMAP. These are protocols. These are standardized, which basically means I can actually run multiple different versions of OpenContrail simultaneously in the live system. You can actually have version 1.03 and 1.02 running simultaneously in the same live environment where the control plane nodes are talking to each other without a problem. You can actually add a new configuration knob, but because we are using IFMAP, which actually represents config as a graph and not as a sequence of instructions, you can add new configuration knobs and it allows you to support both old config and the new config. So there are significant advantages of using protocols rather than APIs which are non-standardized or can be changed by one party unilaterally. The other aspect is physical or software gateway. If you've seen, most of the solutions require a software router to connect from the virtualized world to a physical world, a gateway of sort. In this solution, you can actually use your existing routers, whether it's a Cisco ASR 9K, a Juniper MX, Alcatel-Lucent Trimetra router, or a Huawei router. You can use any of them and seamlessly talk to it because we use BGP. You do not need any new version of software. Actually, in our lab, before we were acquired by Juniper, we were running software from 2004, and we could show traffic going from virtualized world to non-virtualized world seamlessly. In addition, for people who actually don't want to invest in expensive hardware, especially for POC purposes, we also provide a software gateway, which allows you to connect a public network to a virtualized network. I don't think it's really for production use, in the sense that production systems require gigabits of traffic. This thing can only do 10 gig, and it is scale out, so you can actually add more nodes. But then, as you start adding more nodes, the cost of the system doesn't make sense versus a physical router for that purpose. The next aspect is analytics, and it's something that I really recommend you to go and see the demonstration. It actually is extremely powerful engine, and it allows you to do lots of really interesting stuff. You can write your own Hadoop job to mine the database. You can actually write your own DPI engine or your own DDoS engine using the analytics subsystem. We have customers that are actually doing that. Service chaining is another unique aspect of the design. What you can do is you can say that all traffic going from VLAN 1 or virtual network 1 to virtual network 2 needs to go through a firewall. And that's all you have to do. You have to describe the policy at a high level. It's not a complicated security group kind of rule. It's a very, very simple policy. And that policy will actually get described in the system and will get translated down into what actual version of physical firewall or virtual firewall you're using. It will monitor the load in the network. If the network load starts to increase, it will spawn new instances of the virtual machine providing the firewall service. If the VM dies, it will restart it, and because we have load balancing built into it, it will make sure that only the new flows go to the new virtual machine and the old flows don't get reordered. So service chaining on the high level sounds very easy, it sounds very simple, but it's actually a very complex thing. It is doing service monitoring, it is doing service scale out, it is doing load balancing, and it is creating VLANs or VRFs or VPNs on the fly and leaking routes into those VRFs to connect all of them together. But you will not have to worry about it. All of this is done under the hood. And we already discussed the availability story. And the API, everything is done using APIs. There is no CLI in the system. Even the CLI, whatever limited CLI we have, is built using the API. Now let's look at the physical topology of the system. If you look at the compute nodes, we've actually replaced the OVS or a Linux bridge with a virtual router. This is a very important concept to understand. We've actually replaced OVS or a Linux bridge with a vRouter. It's running in the kernel and it is very high performance. It does GRE tunneling at line rate. That's another innovation we have done. It doesn't require any new protocol like STT, which doesn't work very well over WAN, and it doesn't work very well even within the LAN from a firewall point of view. We can do that with very limited impact on the CPU utilization. And this is the way we have done this, actually very interesting. What we realized is that the amount of CPU utilization for doing TCP offload engine was not a lot. And doing that in hardware just didn't make sense because now you're tied to the device you're using, you're tied to the NIC you're using. So we said, why don't we just do it in software? It only has 5% impact on a single core. And I can get full TCP segments from the VM, from the guest. And in addition, if I have one packet loss over WAN, even with 0.1% or 0.5% packet loss over wide area network, all I have to do is retransmit just that packet. I don't have to retransmit the whole packet. So the vRouter is fairly complex. It does full fragmentation and reassembly. It does full TCP offload engine in software with limited impact to the CPU performance. And the control plane nodes, the configuration nodes, and the analytics node are all obviously running in software. What you will notice here is there is no software gateway. The only reason for that software gateway is for POCs. Typically what you would do is you will have the controller talking directly with an edge router using BGP. And you would typically configure the public network only once on that PE router. If you want to create new VRFs all the time, you can use netconf, and we support netconf. We have netconf scripts that you can use to configure the router every time a new VRF needs to be created. To the server, we do not use BGP because BGP is complex and it's harder to maintain. So what we do is we run a very small, limited scale BGP state machine, and we send, using XMPP in an XML format, all the messages down to the virtual router agent. The other thing we do on the XMPP link is send all the configuration. So you have one socket interface from the compute node to the control plane node for transferring all the routing information, for all the policies, and every other feature that we provide in the system. And this is probably the most important feature, is we can route and bridge straight from the hypervisor in and out of a virtualized to physical environment in a seamless manner. And we use different tunneling technologies depending on the endpoint. So for example, the vRouter will talk to the PE router or rather the controller will tell the compute node that the V router needs, when traffic is going to the PE router, it needs to use MPLS over GRE, for example, as a tunneling technology. Or it needs to use VXLAN as a tunneling technology because that's what it supports. So BGP has this concept of next hop attributes, and you can basically send information using that to tell the compute node what tunneling technology to use depending on whom you're talking to. So when I have two V routers talking to each other, it will probably use MPLS over UDP because that's the highest performance solution out there, and it uses the best ECMP over the fabric. But when it is talking to a PE router, it will actually end up using MPLS over GRE because that's the most commonly used protocol in the routers today. Maybe this year or next year it will become VXLAN, and then we'll support VXLAN. Obviously, you can use VXLAN also when you're crossing from one compute node to another. And the other thing that I described is service chaining. So you can actually describe in the policy definition that all traffic coming from the public internet hitting any of the web front ends needs to go through a F5 firewall and then a Juniper SRX firewall. And this could be a virtual machine or it could be a physical machine. This capability is not there in Neutron today, so you can only use it using OpenContrail APIs. But as we get to Juno or maybe beyond Juno and community accepts the new extensions, we will get the capability of doing service chaining in the OpenStack natively. So I encourage you to go and see the demo. I'll keep the last 5 minutes for questions, but before I go there, I'll talk a little bit about OpenContrail. It's available in open source. It's completely integrated with OpenStack. You can get the DevStack scripts from opencontrail.org. You can add extensions to it. You can submit a GitHub pull request and it will get committed once it gets reviewed. It is the same as a commercial product. The only difference between OpenContrail upstream, downstream is validation. We just run a lot more regression tests on our downstream release that we sell as a supported Juniper solution. But you can obviously use the upstream version, and we are going to get to a lot of stability fairly quickly. We are also going to add community release fairly soon. So our goal is just like Ceph is going to have a Firefly release, we will have a similar community release coming up for OpenContrail that is very stable, that you can actually deploy in your production network. The license is very permissive. It's Apache v2 for controller and it's GPL for vRouter. We're actually working also on a FreeBSD license for the vRouter so that you don't have to, if you make changes, you don't have to contribute it back if you don't want to. And it's completely integrated into OpenStack. If anybody of you even cares about CloudStack, obviously you can go get it from the beta site as well. So that's all. I'll take a pause here. If there's any questions, please feel free to ask me.
質疑応答を受けさせていただきます。ご質問あります方は挙手をお願いいたします。ただいまマイクをお持ちいたしますので、どなたかいかがでしょうか。よろしいでしょうか。どなたかいらっしゃいませんか。それではご講演を終了とさせていただきます。どうもありがとうございました。シングラ様、Thank you very much.